Our next theorem that we're going to study in this course is the so-called Bolzano-Weierstrass theorem. This theorem is a really interesting one, and it's very simple to state. And so we'll quickly have a look at what it is, and then we'll develop a bit of a proof for it. So here it is. Here's our theorem. Every bounded sequence has a convergent subsequence. That's it. It's the whole thing. Okay, so maybe before we try and prove it, we should try and understand a little bit about what that actually looks like. So we have a sequence. It has to be bounded. So maybe your mental picture for a bounded sequence is you've got some bound m down to minus m. And for a sequence to be bounded, it says nothing about it apart from the fact that all the terms must fit between these two limits. It says nothing about what terms close to each other do or anything like that, but our sequence consists of terms that are between minus m and m. There is a bound m that we can call into play should we need it. Okay, so that is the kind of sequence we're looking at, and what the theorem tells us is actually every single sequence that's like this has a convergent subsequence. So maybe we can imagine that if we pick out some specific elements, maybe these ones, over time we can choose a subset of the elements that do actually converge to some particular limit. Now there might be a different subsequence that converges to a different limit. That's entirely possible. But the remarkable thing about the theorem, it says that no matter what set of random points we throw in there, if they're bounded, then we'll be able to extract a convergent subsequence no matter what. So it says something about how the real number line behaves, that no matter how we distribute our points, we are always able to extract a sequence like this from it. So to get started on this, we're going to have to first produce a subsequence that we can show converges to some particular limit. Okay, so this one's, we've got to get a little bit creative here. So to start off with, I'm just going to draw my number line here. Here are the real numbers, and I've got 0 here. So we've got let AN be a bounded sequence. Okay, so if it's bounded, it means that we can have a bound. So I'll let that be m minus m. So just going to sort of sketch out our ideas first before we go and throw it down into a properly worded proof. So here's the interesting thing about the construction we're going to use. So we have to make a subsequence somehow out of our sequence, knowing next to nothing about it. All we know is that it's convergent. We don't know it's convergent. All we know is that it's bounded, our sequence, and nothing else. So what we do is we say, all right, we're going to use the nested interval property to build ourselves a subsequence. So what we do first is we split our interval into two. So that's going to be the interval minus m up to m into two pieces, minus m0 and 0m. And we're going to build a whole set of nested intervals that will contain something useful. So I'm going to call this interval here I0, my original one, and I'm going to call the first interval I1. And the way I'm going to choose between these two to make my nested interval sequence is because we have a sequence, it means we have infinitely many terms in our sequence. And because I want my process to be able to go on indefinitely into smaller and smaller pieces, I'm going to choose one of these to have infinitely many the one that has infinitely many terms. Now maybe they both do, in which case I can just make a random choice, but choose one to have infinitely many terms. So our sequence has infinitely many terms in it, and so at least one of those halves also has to have infinitely many terms. Alright, so let's say for sake of argument that we got this half here. This will be our interval I1. Let's make I0 a different color on our picture. Maybe here is I0. And then we're going to choose I2 in the same way. So maybe this one here is I2 and I3. etc. At each step, we split ik in half and choose ik plus 1 to be a subinterval containing infinitely many terms. So hopefully the process of choosing our sequence of nested intervals kind of makes sense. We're just dividing our containing interval in 2 each time, and we're going to take a half that has infinitely many terms of our original sequence left in it. Okay, so far so good. So we've got this stacked set of intervals, and we know from the nested interval property that there will be some number guaranteed to be inside the intersection of all of these intervals. That number is going to be the limit of the sequence we're going to design. So by the nested interval property, there exists x in ik. How about we say that? There exists x such that x is in ik for all k in the natural numbers. Oh, and 0, I suppose. Okay, so our nested interval property tells us that we're going to have an x that's in each one of these, and this is going to be our candidate for our limit for our subsequence. Alright, so we don't actually have a subsequence yet. We've got a stack of intervals, and we've got a point in all of them. Now we need to build a subsequence that makes sense. Remember that a subsequence has to respect the order of the original sequence. So we're going to choose a point in each one of these intervals, and we're going to choose our point or our sequence term so that it's in each time we have infinitely many terms to choose from, so we can always go a little bit further on in our original sequence when we make a choice of a point. Okay, so at the moment we've got our limit candidate. Let's just label that. What else do we need? And we're going to choose a in 1 to be in I1. Okay, so that's easy enough. So now we're building our subsequence. We're going to choose a in 2 to be in I2 with n2 bigger than n1. Note, because we have infinitely many terms in there, this is always going to be possible. And then we'll choose a in 3 to be in I3 with n3 is greater than n2, etc. So here is our subsequence a in 1 a in 3, and here is our limit candidate x, which is the thing that's in all intervals. What else do we need? We don't really need anything else. We just need to now go and show that this subsequence converges to our limit x. So we've designed a subsequence, we have produced a candidate for its limit, and now we need to use the definition of the limit to show that it converges. Okay, so perhaps we should maybe write a slightly tidier argument as to how this all goes. So I'm just going to put that up really quickly. Okay, to spare you having to watch me do it, I just wrote down what we've done so far in slightly more structured language. So we started off by defining ourselves a bounded sequence. That in turn let us choose an upper bound, which is good. Then we construct a sequence of intervals, that's this part here. And we did that in such a way that we always have infinitely many terms in each piece of the intervals. Okay, and we use those intervals to construct a subsequence of our original sequence, and then we have a candidate limit that we are going to show that our subsequence converges to. Okay, so this is quite a nice proof in that it actually provides us with a method of constructing our subsequence, and it provides the point using the nested interval property that we're going to show it converges to. So at this point in time, we're now in slightly more familiar territory. We've done our weird thing, which is to construct this set of intervals with a certain property, and we can construct our subsequence. That's great, and we've got a limit point to compare with. So now we're going to do our normal thing, which is to show that this sequence converges to x. So now we're going to do this part. Let epsilon be greater than 0. We seek n such that, now just get the language right, absolute value of a in k minus x is less than epsilon whenever k is greater than or equal to n. Okay, don't forget k is the index for our subsequence, so I'm going to state it as k, not little n here. Alright, so we've got ourselves an epsilon fixed, and now we're going to look for an n. Okay, how do we do that? Well, turns out that's not too hard either. If we look at our intervals again, let's just look at the length of the interval k. So length of interval k. So if we go k equals 0, clearly when our first interval was just negative m up to m, so it's got width 2m. If k equals 1, it's half as big again. K equals 2, it's m over 2. K equals 3, it's m over 4. Continuing on, we get 1/2 to the power of k. I guess we'd be correct by a constant factor just to make sure it works. If k equals 1, it should be m, so that should be a 2m out the front. Alright, so the length of interval k is actually a sequence itself that converges to 0. We've showed that 1 over n, for example, converges to 0, and 1/2 to the k is definitely a subsequence of that. So this thing converges to 0 as k goes to infinity, which means we can choose our n to make this as small as we like. So let's just write that down. So we'll choose n so that k is greater than or equal to n implies that the length of interval k is less than epsilon. Okay, I'm not even going to try and figure it out in terms of the powers of 2 and things like that. Just going to use the fact that the length of the interval is a convergent sequence. So I can choose my interval length. I can choose n so that my interval length is as small as I want it to be. Why would I want to do that? Well, if my interval is smaller than epsilon, so here's ik, maybe this is epsilon, distance along here, then it's definitely the case, remember a n k is just a point inside that interval, and so too is x. This distance here is guaranteed to be less than epsilon if I choose my n this way. Right, so that is the next part of the convergence proof. State what we want to do. Now we choose n, and we've got ourselves a choice of n now. I'm going to write this down. Choose n. Choose means some property of something has guaranteed that this exists. So choose n such that k is greater than or equal to n implies that the length of ik is less than epsilon. And I'll just make a little note here. Length of ik equals 2m half to the k, which converges to 0. Just to justify that choice of n there. Okay, so that's great. This implies that the absolute value of an minus x, ank, sorry, minus x is less than epsilon, and hence our subsequence an sub k converges to x. Okay, so this particular proof had quite a lot of setup involved. We had to come up with defining our subsequence in quite a clever way. And we made heavy use of the fact that sequences have infinitely many terms. The reason we did that was so that we could always choose these elements here. Okay, we could always choose an2 with n2 greater than n1, and an3 with n3 greater than n2, etc., etc. Why do we want to do that? Well, otherwise it wouldn't be a subsequence. And if at some point we had an interval with finitely many points left in it, then we may not have been able to choose a high enough number n to make it work. Okay, so we made heavy use of the fact that we have infinitely many points in our sequence. We just designed ourselves a subsequence that had length converging to 0. Didn't matter exactly how we did this. Any way of choosing a subsequence that has length tending to 0 with infinitely many terms in each interval would have worked. It's just this one is convenient. And then we used the nested interval property to actually get the existence of a point in each one that was allowed to be our candidate limit point. From there, the actual process of verifying that the subsequence we had produced converged, unlike some examples, actually proved to be relatively straightforward, because we just chose a small enough interval so that a and k and x were forced to be close enough together that it was all going to come out for us. And that is the Bolzano-Weierstrass theorem.